Okay, when you go to graph polynomials using non-calculus methods, that is, you're in a pre-calculus course, most polynomials you can't touch. You know, you'd have to go to the graphing calculator, for instance. This isn't too bad. You could look at this and start and think, well, the y-intercept, how do you find? Enter, I'm going to use the word enter for y-intercept. You set x to 0 and you get 3, right? So when x is 0, y is 3. That's pretty easy to find. And you can do the lead term test on this pretty well. The highest powers dominate on these polynomials, so it's going to behave like x cubed, and we know how x cubed looks. You know, it goes off to infinity this way and off to infinity this way. But really, to get any kind of picture of this, you need to find x-intercepts, and that's just not possible. You know, I mean, you could, this probably doesn't have rational roots. In fact, I know it doesn't, but most any polynomial right doesn't have rational roots, and you can't factor it. What are you going to do? You can't get a decent picture of this thing. But there's a nice little trick you can use to draw a pretty good graph of this. What you do is you define this as y equals g of x plus 3, where g of x equals x cubed. Okay? X cubed plus 5x. X squared, sorry. Where g of x is this part. Okay? Now we can graph g of x. And if we can graph g of x, we just have to raise it up 3. And that's the basic procedure here. So I have to graph g of x, and once I understand g of x, I realize that y, my original function, is just g of x plus 3. So y-intercepts, very, very easy. Set x to 0, and I'm going to use enter here. You set x to 0, and you get 0. 0. Okay. The lead term test is still the same. Highest power dominates, right? X cubed, so it's going to look like x cubed. So it's going to go off like that. All right. I'm drawing a little graph here because we don't know what goes on in there, but we've got that. And then x-intercepts. All right. Now you notice I can factor g of x. Okay, x enter. I'm going to use that as so, in fact, I'm going to write this as in factored form. I'm going to say x squared. I can factor an x squared out of here. I'm left with x plus 5, aren't I? And I set that to 0. Put the y to 0. And I see that if I set this to 0, x will be 0. And here are my x-intercepts, 0 and 0 and negative 5. If I set x plus 5 to 0, I'll get a negative 5. So I have negative 5 and 0, like that. And this one bounces, right? This one will go through. And why? Because this is to the first power. That's an odd power. This is an even power, so the even powers bounce when they hit the x-axis, whether they come from above or below. So I've got all this information on g of x, and I can graph g of x. Now, stop the video and write that down, because I'm going to erase it, because I want to be here in the board when I draw my graph. We're going to draw g of x plus 3, okay? Okay. Wow. First of all, we're going to g of x plus 3. We have to raise the whole thing up 3. And I draw a dotted line, a fake x-axis, and I call it x hat, so I know that it's not a real axis or some kind of horizontal asymptote or something. So that's what it is. Now I realize I'm going to pretend that this is the origin. Notice I have, if you look back, the x-intercepts were on g of x were 0 and 0 and negative 5. Here's negative 5. 1, 2, 3, 4, 5. Yeah. All right, it goes like this. We know it comes from up here. We know it comes down here. It bounces, doesn't it? We don't know how high it goes, but we know it has to come back and go something like this. And there is g of x plus 3, or y equals x cubed plus 5x squared plus 3. A pretty good graph of that. I can even guess where this x-intercept is. I'd say, oh, maybe negative 6.5. And there we've taken, you can do this with a lot of these. You know, you can factor out You can just call it g of x and you can get an idea, and it just moves it up and down. And this gives you a whole bunch of more polynomials that you can take a look at with pencil and paper graphs.